This is the split criteria, which is hard dollar target. That is, I want to split this data frame with respect to this target column. And the split ratio which I'm stating over here is 0.7. That is, 70% of the records would have the true label associated with them, and the rest 30% records would have the false label associated with them. And the final result, I am storing it in split tag. Now, what I'll do is, from the entire hard data frame, whichever records have the true label associated with them in the split tag, I'll take all of those records and I'll store them in the training set. Similarly, from the entire hard data frame, wherever the split tag value is equal to false, I'll take all of them and I will store them in the test set. So I have my training and my testing sets ready. Now let me have a glance at the number of rows of the training and testing set. So n row of train, there are 213 rows, and n row of test, there are 90 rows. So now that we have the training and testing sets ready, let me go ahead and build the model on top of the training set. So again, we'll use this GLM function and build the model. So this time the formula is the same, which is basically target tilde symbol age. So target is the dependent variable, age is the independent variable, and we're trying to determine the probability of the patient having heart disease with respect to his age. And we are building this model on top of the train set. And since this is a logistic regression model, the family would be equal to binomial, and I'll store this result in log mod 2. Now that we've built the model, it's time to predict the values. So I'll use the predict function, and this again takes in these three parameters. First is the model which we've just built, and then second parameter is the object on which we want to predict the values. So we want to predict the values on top of the test set. And finally, we'll set the type to be equal to response, which will basically give us probabilities for these predictions, and I'll store the result in pred hard. So let me have a look at the range of the predicted values. So we see that the range of the predicted values of the heart disease, it varies from 0.21 to 0.86. That is, the probability of the patient having heart disease, it varies from 21% to 86%. And this is how we can build a simple logistic regression model on top of this heart disease dataset. Now let's head on to the next question. So what is a confusion matrix? So confusion matrix is actually a table which is used to estimate the performance of a model. It tabulates actual values and the predicted values in a 2x2 matrix. So these are the actual values and these are the predicted values. So this what you see, true positives. So this denotes all of those records where the actual values were true and the predicted values were also true. So these denote all of the true positives. After that, we have the false negatives. So false negatives denotes all of those records where the actual values were true, but the predicted value was false. So where the actual value is true, but the predicted value is false, that is known as a false negative. Then we have false positives. So in false positive, the actual value is false, but the predicted value is true. And such values are known as false positives. And finally, we have the true negatives where the actual values are false and the predicted values are also false. So if we want to get the correct values, then correct values would basically represent all of the true positives and the true negatives. And this is how confusion matrix actually works. So now we are supposed to build a confusion matrix for the model which we built, where the threshold value for the probability of predicted values is 0.6, and then we have to find the accuracy of the model. So as I've already stated, accuracy is basically true positives plus true negatives upon all of the values. So this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been incorrectly classified. So when we divide the left diagonal with all of the values, that is when we'll get the accuracy of the model. So let's go to RStudio and find out the accuracy of the model which we built. So to build a confusion matrix in R, we'll be using the table function, and inside the table function, first we'll give in the actual values and then we'll give the predicted values. So the actual values are stored in this target column of the test set, and the predicted values are stored in the pred heart object which we had created. And then we saw that the range of the probabilities, it was from 0.2 to 0.8. So from that range of 0.2 to 0.8, I am setting a probability threshold of 0.6. That is, wherever the probability is greater than 0.6, it will be classified as 0, or in other words, it will be classified that the person does not have heart disease. And similarly, wherever the probability is less than 0.6, it will be classified as 1, or in other words, that the patient has heart disease. So I'm reiterating it again. So wherever the probability of pred heart is greater than 0.6, it will be classified as 0. And wherever the probability of pred heart is less than 0.6, it will be classified as 1. So let's go ahead and build a confusion matrix. So you see that this is our confusion matrix, and this left diagonal represents all of those values which have been correctly classified, and this right diagonal represents all of those values which have been incorrectly classified. And if you want to find the accuracy, all we have to do is divide this left diagonal with all of the values. So that'll be 31 plus 17 divided by 31 plus 17 plus 10 plus 32. So you see that we get an overall accuracy of 53% for this model which we built. Now let's head on to the next question. So what do you understand by true positive rate and false positive rate? So let's start with true positive rate. So in machine learning, true positive rate, which is also referred to as sensitivity or recall, is used to measure the percentage of actual positives which are correctly identified. So the formula for true positive rate is true positives divided by all the positives. So I am stating it again. True positive rate is basically the measure of the percentage of actual positives which have been correctly identified. Now let's look at false positive rate. So false positive rate is basically the probability of falsely rejecting the null hypothesis for a particular test. So the false positive rate is calculated as the ratio between the number of negative events wrongly categorized as positive, that is all of the false positives, upon the total number of actual events. So this is how we can calculate true positive rate and false positive rate. Now we have the next question, and we are supposed to explain what is ROC curve. So ROC curve, which actually stands for receiver operating characteristic, is basically a plot between the true positive rate and the false positive rate. And it helps us to find out the right trade-off between the true positive rate and the false positive rate for different probability thresholds of the predicted values. So the closer the curve is to the upper left corner, the better the model is. Or in other words, whichever curve has greater area under it, that would be the better model. So let's say we have this curve over here, and let's say there is another curve which goes like this, which is nearer to this upper left corner. Then in that case, since the second curve covers greater area under it, that would be a better model than the first model. So this ROC curve helps us to find out the area under the curve as well as the right trade-off between the true positive rate and the false positive rate. Now we are supposed to build the ROC curve on top of the logistic regression model which we've built. So let's head back to RStudio and do that. So to build the ROC curve, we would have to load the ROCR package. So I'll use the library function and load up the ROCR package. Now, this ROCR package comprises of the prediction function, which would give me a prediction object. So this takes in two parameters. First parameter is all of the predicted values. So this pred heart comprises of all of the predicted probabilities for the target column. And the second parameter is the labels of the dependent variable. So test $target has all of the labels of the dependent variable. And I will store this result of the prediction object in ROC pred heart. So now that we've created the prediction object, we can go ahead and build the ROC curve. And to build the ROC curve, we'll use the performance function, which is again a part of the ROCR package. So this over here takes in three parameters. First is the prediction object, which you built. So the name of the object was ROC pred heart. After that, we will just give in TPR and FPR. So TPR and FPR stands for true positive rate and false positive rate. So for this prediction object which we built, we are basically trying to find out the right trade-off between the true positive rate and the false positive rate, and I'm storing the result in ROC curve. Now let me go ahead and plot this ROC curve which I've just built. So this is our ROC curve over here. Let me zoom this. So we have this curve for different probability values over here. So this, what you see are the different probability values. And our ideal curve should be something like this, where we have more of true positives and less of false positives. And this green color which you see, so this green color actually represents the ideal threshold value. So the ideal threshold value over here would be somewhere between 0.48 and 0.62. So this is where we would have the ideal threshold value of the probability. And this is somewhere where we can get the right trade-off between the true positive rate and the false positive rate. So maybe it could be this over here. So this point which we see, so the probability would be somewhere around 0.5 or somewhere around 0.55. So this is where we could get the right trade-off between the true positive rate and the false positive rate. So now that we've built a logistic regression model in R, again, we need to know how to build a logistic regression model in Python. So this time we are supposed to build this logistic regression model on top of this customer churn data frame, where the dependent variable is this churn column and the independent variable is this monthly charges column. And after that, we are supposed to find out the log loss of the model. So we are basically trying to determine whether the customer would churn or not on the basis of this monthly charges column. So again, I'll start off by loading the pandas data frame and also load the customer churn.csv file. And for that purpose, I'll be using the pd.readcsv function. Right, so we have successfully loaded the file. Now it's time to have a glance at the head of this data set. So these are the different columns which we have. So we have this customer ID, then we have the gender of the customer, we have the senior citizen column, which tells us whether the customer is a senior citizen or not. This column tells us whether the customer has a partner or not. This column tells us if the customer has any dependents or not, the tenure of the customer, whether the customer has phone service or not, and so on. Sort of all of these columns, the columns which are of our concern would be the monthly charges column and churn column. So this monthly charges column basically tells us the monthly charges incurred by the customer in dollars. And this churn column tells us whether the customer would churn or not. So now since we have our data set, with us, let me go ahead and separate the dependent variable and the independent variable into two separate objects. So I'll store this monthly charges column from this customer churn data frame in the X object. Similarly, I'll store this churn column from the customer churn data frame in the Y object. So we have our dependent variable and independent variable to be separate. Now I'll go ahead and divide this model into training and testing set. And for that purpose, I would require this train test split function, which is part of the sklearn.model selection package. Now I'll use this train test split function, and this takes in these parameters. First are basically the independent variable and the dependent variable. So the independent variable is stored in X and the dependent variable is stored in Y. After that, I'll set the test size to be equal to 0.3. So this basically states that 70% of the records would be in the training set and the rest 30% of the records would be in the test set. And again, I'll set a random state value so that I can use these same values again if I want to. And I am storing all of these values into xtrain, xtest, ytrain and ytest. So xtrain comprises of the training set of the independent variable. Similarly, xtest comprises of the test set for the independent variables. After that, we have ytrain, which comprises of training set for the dependent variable. And then we have ytest, which is the test set for the dependent variable. So now we have xtrain, xtest, ytrain and ytest. It's time to build the model, predict the values and get the log loss value. So first I will import this logistic regression function from this sklearn.linear model package, and I'll create an instance of logistic regression. I'll store it in L and then I'll fit the model on top of the training set. So L.fit, and I'm fitting the model on top of xtrain and ytrain. After that, I'll predict the probabilities on top of the test set. So L dot predict underscore proba, and I'll pass in X underscore test, and I'll store the predicted probabilities in Y underscore pred. So now that we've fit the model and also predicted the probabilities, it's time to look at the metrics. So the question stated that we were supposed to find out the log loss. So I'll just import the log loss from sklearn.metrics, and inside this log loss function, I will pass in the actual values and the predicted values. So actual values are stored in Y-test and predicted values are stored in Y-pred. So we get a log loss value of 0.55. Now again, similar to RMSE, the lower the value of log loss, the better the model is. So again, let's say if there is another model and the log loss value of that second model is less than this, then that second model would be better than this model. Now we'll head on to the next question. So what do you understand by decision tree? So decision tree is a supervised learning algorithm which is used for both classification and regression. Right. So decision tree can be used for both classification purpose as well as regression purpose. So in this case, the dependent variable can be both a numerical value as well as a categorical value. So there is a flowchart like structure where the topmost node is known as the root node, the internal nodes with children are known as the branch nodes, and the final nodes without children are known as the leaf nodes. So here, each node actually denotes a test on an attribute, and each edge represents an outcome of the test, and each leaf node holds a class label. So let's say this first node over here, we are trying to determine the age of the patient. So let's say if the age of the patient is greater than 50. If the condition is true, we'll come here. If the condition is false, then we'll come here. After that, over here, we'll check if the person smokes or not. And if that person smokes, we'll come here. If that person doesn't smoke, we'll come here. Similarly, over here, the test condition could be whether the patient has any children or not. If the condition is true, we'll come here. If the condition is false, we'll come here. So this is how the decision tree works. And finally, we'll have class labels over here. So these would represent individual class labels. So let's say this represents that the person has cancer. This represents that the person does not have cancer. Similarly, this would represent that the person has cancer. And again, this would represent that the person does not have cancer. So in decision tree, we basically have a series of test conditions which would give us the final class labels. Right. So now we have to build a decision tree model on top of this iris data set, where the dependent variable is the species column and all other columns are independent variables. And after we build the model, we are supposed to find out the accuracy of the model. So let's go ahead and do this. So I'll start off by having a glance at the iris dataset. View of iris. So this is our data frame which comprises of all of these columns over here. And to build a decision tree model, we'll be loading the party package. So library of party. So again, before I go ahead and build the model, our task is to first divide this data frame into training and testing sets. So again, I will load up this caret package, library of caret. I'll use this create data partition function, and this create data partition function takes in the species column as the split column, and I'll give the split criteria to be 0.65. That is 65% of the records would be having the true label and the rest 35% of the records would be having the false label, and I'll store that in split tag. Now from the iris dataset, wherever the value of split tag is equal to true, I'll store that in the train set. Similarly, from the entire iris dataset, wherever the value of split tag is equal to false, I'll store that in the test set. Now again, let me have a glance at the number of rows of the training and testing set. So you see that there are 99 rows in the training set and there are 51 rows in the testing set. So now again that the train test split is done, we can go ahead and build a model. And to build the model, we'll be using the ctree function, which is a part of the party package. So this again takes in two parameters. First parameter is the formula. Next parameter is the data set on which we are supposed to build the model. So here the formula is species tilde dot. So this tells us that species column is the dependent variable, and when you put a dot on the right side of the tilde symbol, that basically means that all other columns except the dependent variable are the independent variables. So sepal length, sepal width, petal length and petal width, all of them would be the independent variables and species would be the dependent variable. And again, we are building this model on top of the train set and I'll store this result in my tree object. So now that we've built the model, let me plot it. So plot, and I'll pass in this object, which is my tree. Now let me zoom this. So this is our root node, and the root node, the split criteria is on the basis of the petal length column. So we see that if the petal length is less than or great, so see that if the petal length is less than or equal to 1.9, then we come over here and this tells us that the species of the flower is setosa. On the other hand, if that is not the case, that is, if petal length is greater than 1.9, then we have another test condition over here. So here we check if petal width is less than or equal to 1.7. And if it is true, again we have two scenarios. So here we are checking if petal length is equal to or less than 4.7. So if petal length is equal to or less than 4.7, then there is a 100% probability that the species of the flower is versicolor. Similarly, if the petal length is greater than 4.7, then there is around a 60% probability that the species is versicolor, and there is around a 40% probability that the species is virginica. On the other hand, from over here, if we directly come over here and if we check that petal width is greater than 1.7, then in that case, there is almost a 100% probability that the species of the flower is virginica, right? So these are the test conditions on the basis of which we are trying to determine to which class does the species belong to. So now that we've built the model, let's go ahead and predict the values. So I'll use the predict function again. This takes in these parameters. First is the model which we built. So the name of the model is my tree. And then this is the data set on top of which you want to predict the values. So we want to predict the values on top of the test set. And then finally we want the response. And that response I'm storing in my pred object. Now after this, let me go ahead and build the confusion matrix. And to build a confusion matrix in R, we'll be using the table function. And the first parameter includes all of the actual values and the second parameter includes all of the predicted values. And this is what we have over here. So this denotes all of those records where the actual value is setosa and all of those actual values have been correctly predicted as setosa. So there are 17 such instances. So this denotes all of those records where the actual value is versicolor and all of them have been predicted as versicolor. So there are 16 such instances. And this one denotes those records where the actual was versicolor, but it has been incorrectly classified as virginica. Similarly, this one over here, this states that there is one record where the actual value is virginica, but it has been incorrectly classified as versicolor. Similarly, this 16 which we see. So out of the 16 records which were actually virginica, all of those 16 records have been correctly classified as virginica. Now again, to find out the accuracy, we are supposed to divide this left diagonal with all of the values. So that'll be 17 plus 16 plus 16 divided by 17 plus 16 plus 16 plus 1 and 1. So you see that we get an accuracy of 96% for the model which we've built. Now let's head on to the next question. So what do you understand by random forest model, and also explain the working mechanism of random forest? So random forest is an ensemble model. That is, it combines multiple models together to get the final output. And to be precise, it combines multiple decision trees together. Now let's understand the working mechanism of random forest model. So let's say we have this dataset A and we have n records in it. Now what I'm going to do is draw samples from this dataset. So this actually will be sampling with replacement. That is, I'll take one record from dataset A, take note of it and enter the same sample in dataset A1 and then put the record back to where it came from. And I'll repeat this process n times so that there are n records in dataset A1 as well. So what you need to keep in mind is, out of these n records in A1, some of them might have come twice, thrice, or even several times over, while some records from A might not have made it at all to A1. So I've created A1 like this. Now I'll go ahead and create multiple data sets the same way. And each of these have the same number of records as A. And the X over here, it could be anything. Let's say 100, 500 or 1000. So from just one data set A, we were able to create multiple data sets for our advantage. So just for our sake, let's say the data set A has 1000 rows and the value of X is also 1000. So it would be 1000 cross 1000, which would give us 1 million rows. That is, from just 1000 rows of data, we were able to create 1 million rows. Now for each of these X data sets, we'll fit X decision trees. Now let's say this A1 data set over here has 10 independent variables. So what happens in a random forest is, each time a node is being split in a decision tree, not all 10 columns will be provided to the algorithm. This is important, so I am retreading it, guys. So each time a node is being split in a decision tree, not all 10 columns will be provided to the random forest algorithm. So now the question arises, what would be made available to the algorithm? So only a random subset of these 10 columns will be available to the algorithm. So let's say I want to split this root node now. So instead of providing it all the 10 columns, only a subset of the columns will be provided. So let's say 3 columns, and it could be any 3 out of the 10. And with those 3, the algorithm goes on to split the node. And similarly, from the left node over here, it is again going to be provided with a random set of 3 variables. And it is not necessary that the left node should get the same 3 variables. It can be a different set of 3 columns altogether. So whenever we are splitting a node, it is given a random set of m predictors from the entire predictor space. And the reason this is done is to make each of these X trees very, very different from each other. Now let's say a new record Ri comes our way. Then we are going to pass this record to each of these X trees, and we are going to get each tree's prediction on what class this new record is going to represent. And since we have X trees, we'll get X predictions in total. And to get the final prediction, all we have to do is select that class which would have the majority of the votes across all the predictions of the individual trees. So guys, this is the working mechanism of random forest. So now we'd have to go and build a random forest model on top of this CTG dataset, where NSP is the dependent variable and all other columns are independent variables. So let's head on to RStudio and implement the random forest model. Alright, so let me start off by loading the CTG dataset. So I'll use the read.csv function and load this file. Now let me have a glance at this data. So view of data. So this is our dataset which has all of these rows and columns. And this is our dependent variable where we have these 3 values, 1, 2 and 3. So this 1 basically means that the person does not have cancer, 2 means that the person is suspected to have cancer, and 3 means that the person has cancer, right? So these are the 3 different levels associated with this NSP column. Now, let me have a glance at the structure of this dataset. So structure of data. So you see that this NSP column is actually an integer. So we'd have to go ahead and convert this integer type into a factor. So I'll use the as.factor function and convert that NSP column from an integer to a factor, and I'll store that back to same column, data $NSP. Now let me have a glance at the structure of it again. So structure of data. So see that initially this column was an integer. So using the as.factor function, we have converted this into a factor with 3 levels. Now let me have a glance at the frequency of the values of this NSP column. So see that there are 1655 patients who don't have cancer, 295 patients who are suspected to have cancer, and 176 patients who do have cancer. So now, before we go ahead and build the model, we are supposed to divide the data set into train and test sets. So first we'll set a seed value. So that seed value would be 1, 2 and 3. Now I'll go ahead and create the data partition, and the split column is basically this NSP column, and the split ratio which I'm giving over here is 0.65. That is 35% of the records would be in the test set and the rest 65% of the records would be in the training set. And I'll store this in split tag again. Now from this entire data object, wherever the value of split tag is equal to true, I'll store all of those records in the train set. Similarly, from the entire data object, wherever the value of split tag is equal to false, I'll take them and I'll store them in the test set. So we have our training and testing sets ready. Now again, let me have a glance at the training and testing sets. So n row of train, there are 1383 records in the training set. Similarly, n row of test, there are 743 records in the test set. So now that we've divided the data into training and testing sets, I can go ahead and build the random forest model. So for that purpose, I'd have to load the random forest package. So I'll use library of random forest and I'll load up the random forest function. Now again, I'll set a seed value and the seed value would be 222 and I'll build the model. And I am building the model on top of the train set. So I'm using the random forest function. And this random forest function again takes in two parameters. First parameter is the formula. Second parameter is the object or the data set on which we are supposed to build the model. So the formula is nsp tilde dot. That is, this nsp column is our dependent variable and all other columns would be our independent variables. And we're trying to determine whether the person does not have cancer, is suspected to have cancer or has cancer with respect to all of the other columns. And we are building this model on top of the train set and I am storing this result in the RF object. Now that we've built the model, let me go ahead and predict the values on top of the test set. So again, I'll be using the predict function. This again takes in two parameters. First is the model which we've just built. So the model which we built, the name of that model was RF and we are supposed to predict the values for the test set. So I'll give in test over here and I will store the result in the P1 object. Now let me build a confusion matrix for this. So table, and this table function will take in the actual values and the predicted values. So the actual values are stored in the NSP column of the test set and the predicted values are stored in the P1 object. So this is what we have. So this left diagonal represents all of those values which have been correctly classified. So this 567 which you see, so this represents all of those records where the patient actually did not have cancer and it was correctly classified by the model that those patients did not have cancer. So this 8 which you see, this tells you that there were 8 patients or 8 records where the patient did not have cancer, but then again it has been predicted that the patient is suspected to have cancer. Similarly, this 4 over here, it represents those records where in actuality the person did not have cancer, but it has been predicted that the person has cancer. Similarly, if we take this row over here, this 20 represents all of those records where that person in actuality is suspected to have cancer, but it has been incorrectly classified that the person does not have cancer. And this 81 represents all of those records where the person is in actuality suspected to have cancer and it has been correctly classified. And that is how it goes for the rest of the records. So if we have to calculate the accuracy, we are supposed to divide this left diagonal with all of the values. So that will be 567 plus 81 plus 51 divided by all of the values. So 567 plus 81 plus 51 plus we have 2 plus 3 plus 8 plus 4 plus again 2 plus 5 plus 5. And this gives us an accuracy of 96%. So what I've done is I have divided this left diagonal with all of the values, and for the model build I got an accuracy of 96%. So guys, these are some of the questions which you frequently come across when you appear for data science interviews.